Hello again. Just to review what we had done yesterday, we had tried to solve the free vibration equation subject to the initial conditions, displacement at time t equal to 0 and velocity at time t equal to 0. And we saw that the solution to this equation turns out to be equal to u of t is equal to C1 sin omega t plus C2 cosine omega t, where C1 and C2 are real constants. And these real constants can be obtained from these initial conditions in this particular way. Put u at t equal to 0. If we substitute that, this becomes sin 0 plus C2 cosine 0, which is equal to C2 into 1, which implies that u0 is equal to C2 into 1, which implies that C2 is equal to u0. Now, how do we compute? So, we have already got C2 is equal to u0. How do we get C1? For C1, we need to differentiate u of t. If you differentiate u of t, you get u dot of t is equal to C1 omega cosine omega t minus C2 omega sin omega t. Again, substituting u dot at time t equal to 0, we get C1 omega into 1 minus C2 omega into 0, which implies that u dot 0 is equal to C1 omega, which implies that C1 is equal to u dot upon omega. And therefore, the final solution to this equation turns out to be equal to u of t is equal to u dot omega sin omega t plus u0 cosine omega t. This is the solution, complete solution to this equation. If you look at this term, what does it look like? How does it vary with time t? T u of t. If you look at it, it starts at u0. So, this is u0, where if you look at this time t, it is equal to 2 pi upon omega. Okay. So, if you look at it and over here, as we know, this is u dot 0. So, if you look at the amplitude, the peak amplitude, okay, which is u max is equal to u0 squared plus u dot omega whole squared. This is u max. This is the amplitude of the displacement, and the amplitude of the displacement is given in terms of the initial displacement and the initial velocity with the ratio of omega. Okay. Now, there are certain things that are important to look at over here. Remember that omega, as we had defined it, was given as root k over m. This is known as the circular frequency of the structure, and it is given in radians per second. This is known as the time period of the structure and is given in seconds. We have another term defined as omega f, which is omega upon 2 pi, which is known as the frequency and is given in hertz. So, this is defined in seconds, the circular frequency defined radians per second, and f is given in hertz. Now, one important point over here is that omega, which is strictly the circular frequency, is also known as a frequency. I mean, in other words, omega and f are both frequencies. Omega is the frequency given in radians per second, and f is the frequency given in hertz, and t is the time period of the structure. Now, these are dynamic characteristics of the structure, and note that this frequency is related to the square root of the stiffness upon the mass of the structure. So, in other words, think of a structure that is exceedingly rigid. What do we mean by rigid? Rigid implies that k tends to infinity. If k tends to infinity, then from this equation you will see that omega, if k tends to infinity, omega tends to infinity. So, in other words, if you have rigid structure, this implies k tends to infinity, which implies omega tends to infinity, which implies f tends to infinity, and which implies t tends to 0. If you have an extremely flexible structure, which implies k tends to 0, which implies omega tends to 0, which implies f tends to 0 and implies t tends to infinity. So, in other words, it is interesting that if you have a rigid structure, it is characterized by a 0 time period or infinite frequency. In other words, what we are saying is that a rigid structure, when it vibrates, it vibrates in this fashion, and an extremely flexible structure will vibrate where the time period is almost. In other words, if you look at this, does not have a frequency. If you have an extremely flexible structure, you have an extremely flexible structure here, and if you look at this structure, if it is extremely flexible, will actually collapse. If it collapses, what it basically means is that it never comes back. If it never comes back, so in other words, if you look at this kind of thing and I give it an initial displacement, it starts vibrating, and this from this point through this point back to this point and back here is one time period. Do you understand? Start here, you give it an initial displacement, it goes here and comes back here. This is one cycle, or we could also say that it if we look at this, if we give it initial displacement, it comes here, this, from here to here, here and back again is one time period. Okay. So, if you are saying that this time period is infinity, that means it has 0 frequency, what we have is essentially it never comes back. Whereas, if you have an extremely rigid structure, it is vibrating so fast that you cannot see it. Okay. That is t equal to 0, it is practically not vibrating, because it is extremely rigid, okay. It is not vibrating, and therefore, it has infinite frequency because it is not vibrating. Okay. So, it is actually vibrating with infinite frequency. Later on during this course, we will actually take you to a lab and show you what I am talking about right now. Okay. So, coming back to this, in a sense, if we solve this equation, what we get is this kind of a variation. So, if you look at it, if I draw this in a longer time stamp, so here what you are getting is that this are all the same. So, this is essentially because if you look at this, this is just a harmonic function. So, harmonic function implies that the peak and this peak is given by this. Okay. This will remain for all times. In other words, if we go back to what I am looking at, which is it is vibrating in this way, it will keep vibrating. Once I give it an initial displacement and it starts vibrating, it will keep vibrating. That is what this equation, then this is what happens, and it keeps going on and on and on and on and on. Okay. So, once I vibrate it, it will keep vibrating forever. Now, in the real world, this does not happen, right, because you must have vibrated systems and you have seen that they start vibrating and then they slowly decay and they slowly come back. So, in other words, in the real world, what we see is we have a decaying amplitude. We have amplitudes continuously decaying. Okay. So, how do we model this particular kind of behavior? Obviously, this behavior is not the same as this behavior, and so therefore, the equation of motion is not this, because if it is this, then the solution is this, which then becomes this, and it does not reflect the real world situation. In a real world situation, what is happening? If we look at this, this is actually what is known as a classical situation, in which we have a situation where this equation can be written as m u double dot is equal to minus k u. So, what we have is we have equilibrium between the inertial force and the elastic force. This is the elastic force in the columns, and this is the inertial force. Okay. Now, what happens essentially is that we have equilibrium between the inertial force and the elastic force. And what we have over here in this kind of a situation is, when it is at this point, okay, if you look at it, the velocity is 0. The velocity is 0, this system actually represents a conservative system, where at this point, since velocity is equal to 0, kinetic energy is 0, and potential energy is maximum. At this point, potential energy is equal to 0, kinetic energy is maximum, and so therefore, what you have is a constant energy which is given by the initial displacement and initial velocity, and what you have is the energy input by this system then essentially becomes the energy that is supplied into the system. At any given time anywhere here, there is a certain amount of potential energy plus kinetic energy which is equal to the input energy. Okay. At this point, the kinetic energy is 0 because the velocity is 0, but the potential energy is maximum because amplitude of u is maximum. So, potential energy is maximum. At this point, since the displacement is 0, potential energy is equal to 0, but you have the maximum velocity, and so kinetic energy is a maximum, and same way at these points potential energy is 0, kinetic energy is maximum. At these points kinetic energy is 0 and potential energy is a maximum. So, in other words, we are not losing any energy in the system, and we know that a real structure always has an energy loss system built into it. If you look at this particular system, what does it show? That you input a certain energy, okay, that is fine, that energy shows up at this point, kinetic energy 0, potential energy maximum because it is a maximum displacement and 0 velocity. Okay. And what you have ultimately is the fact that this energy, since it starts dissipating, there is some energy loss in this structure, which we are not modeling by taking this equation. This equation is not complete because it does not it only says that energy once input is only changing between kinetic and potential energy, and that is all. Okay. So, therefore, the energy loss in the system is not modeled. Now, how do we model the energy loss? Now, this is a fundamental problem that you have in structural dynamics. The energy loss mechanism is not obvious. Now, since it is not obvious, we do not know how to model it. So, what people have done is that they have postulated, and this is, I want to be very, very clear about it, that nobody still understands what the energy loss mechanism in a structural system is. We know that once it starts vibrating, it's the energy dissipates over a period of time till it comes back to rest. So, we know that there is an energy loss system, but we still do not know, even today, we still do not know what that energy loss mechanism is. So, once we do not know, we start postulating, because there is an energy loss, and as long as you cannot model that energy loss in your equations of motion, then all your responses etc. that you get for dynamic loading is going to be erroneous, because the only equation that you have here is this equation, and if you put this p here, what happens? Well, that solution does not, if we get this solution for a loading p, it still does not incorporate the energy loss in the system. So, the u that we get from that is going to be erroneous. So, it is very, very important for us to be able to model the energy loss. So, how do we model the energy loss? Now, here I must add that there are various models for energy loss in the system, and this energy loss is actually classified as damping. So, what we say is this energy loss is by damping, because what you are essentially doing is you are essentially damping out the vibration of a structure. Since you are damping out the vibration of the structure, this is called, this energy loss mechanism is called damping. Okay. So, how do we model structural damping? This is the major question. Now, when people looked at real life problem and realized that there was a structural damping in the system, you see the basic equation that we looked at, you saw that the equation mu double dot plus k u is equal to p is the same as for the mechanical vibration system. Remember, I just showed this, and this equation and our structural equation turns out to be the same, right. So, since the equation of this system remains the same, the first thing that we include damping is we take the mechanical equivalent. The mechanical equivalent is a viscous dashpot. A viscous dashpot with dashpot constant C. What is this C? The C is such that the force in the viscous dashpot is equal to C times u dot. So, this dashpot constant and this is a characteristic of the viscous dashpot, okay, is such that F is equal to C u dot. And if I take the free body of the rigid mass, then what we get is P of t k u C u, and therefore, again using the D'Alembert's principle, what we get is the net force, which is P of t minus k u minus C u dot is equal to mass into acceleration. And putting this equation in appropriate terms, we get it as mu double dot plus C u dot plus k u is equal to P of t, and this becomes what is known as the equation of motion of a damped, should I say viscously damped mechanical system. So, this is the equation of a viscously damped mechanical system, which is given by this. Okay. So, this is the mechanical system. So, since this is the equation, what structural engineers say it is, well, let us just take a situation where we mathematically have the same system. So, if we look at the one story, one bay frame with rigid beam and the floor mass m, and these being the two columns. What they said was that the energy loss in this system is actually modeled by a mechanical dashpot. Now, in reality this dashpot does not exist, because after all, have you ever seen a single story building with a dashpot in between? No, it is a single story building with columns, beams and the floor, etc. That's how what we have in our structural system. Okay? And so therefore, this is just a mathematical manner of representing the energy loss that you see in the structural system. So, understand that this is an approximation, and although in a mechanical system the C is the dashpot constant, here C cannot be mathematically defined. So, understand that m is the mass, we can actually get it. K is the stiffness, we can get this. How can we get this? Well, we find out the force that we require to get a unit displacement. So, whatever the force to get a unit displacement, that is the stiffness. So, we can actually measure m, we can measure k in a real structure. We can of course mathematically model it also, m and k. So, either way, like for example, remember I got k as 24 EI upon L cubed, assuming that this is L and these are both EI and EI, I computed this. So, both mathematically and experimentally I can get m and k, but I cannot mathematically define it at all, and experimentally I have no clue what to measure. I have absolutely no idea. So, how does this help? Well, let us go back. Let us look at what I will call it as the free vibration of a damped structure. Okay? We are going to look at the free vibration of a damped structure. So, what is that? Then the equation becomes mu double dot plus cu dot plus ku dot is equal to z, and understand that this is a viscously damped structure. So, the model that we are using for the energy loss is the viscous damping. So, now again this is a solution, this is to be solved for initial velocity, initial displacement, initial velocity. How do we solve this? Well, we go through the same process. U of t is equal to A E S t, right, amplitude into e to the power of s t, and so if we substitute this, where u dot is given as A s e to the power of s t, u double dot is given as A s squared e to the power of s t. If we substitute all of these into that equation and then simplifying it, what we get is m s squared plus c s plus k into A E S t is equal to 0. Now, we have already seen earlier that this is not equal to 0, because if this is equal to 0, we get back the trivial solution. So, this is not equal to 0. If this is not equal to 0, obviously, for this equation to be always 0, it is implied that this has to be equal to 0. So, you see, this equation is identical to what we had obtained earlier, excepting for this additional term. And this additional term is going to make it a very interesting solution. So, now let us see. Well, S, this is a quadratic equation and we can solve for this by minus b upon 2a plus minus 1 upon 2a square root b squared minus 4 A C. So, you see this is the quadratic. I mean, this is B, C is B, right. A squared plus B plus C is equal to 0, S is equal to minus B upon 2A plus minus 1 upon 2A square root of B squared minus 4 AC. So, that is all I have done. I have just substituted all these terms in. Okay. Now, what I am going to do is, I am going to actually put this inside. Okay. So, if I put this inside, what I get is minus C upon 2m plus minus C upon 2m squared, because 2m, when you put it inside, you get 4m squared. So, when you put 4m squared over here, you get k upon m. Now, note that earlier we have defined the natural frequency of the structure omega as square root upon k upon m earlier, right. So, which basically means omega squared is equal to k upon m. So, I can substitute this for here, and what I get is this solution. The solution turns out to be S is equal to minus C upon 2m plus minus C upon 2m minus omega squared. Now, you see how this solution is depends on this term. If C upon 2m squared minus omega squared is greater than 0, then S you have 2 real roots of this equation, because if this is greater than 0, then what you get is plus minus square root of a real number which is greater than 0, and so this entire S is 2 real roots. If C upon 2m minus omega squared is equal to 0, think of it, this is 0. So, what you have is a S has 1 real root, and if then S has 2 complex roots. Why? Because if this is less than 0, then this becomes a negative number, and square root of a negative number will become I times the omega squared minus Cm upon 2 whole square. Okay. So, therefore, we see that how C, the value of C actually determines whether what kind of form the solution takes. Okay. So, therefore, this C is a very critical parameter, and what we say is we define a parameter zeta, which we call as C upon 2m omega, right. This is a parameter. I am defining a parameter. This implies then that C upon 2m essentially then becomes zeta omega. Okay. Now, this term is actually called as the viscous damping ratio. Okay. So, this is known as the viscous damping ratio. And what is it? It is a ratio of the dashpot constant 2 m omega. So, in other words, we call C critical as 2 m omega. Think about it. C critical is 2 m omega, and essentially zeta becomes a ratio of C to C critical. Why is C critical 2 m omega? Let us come back to this. Okay. In other words, if C is C critical, xi is equal to 1. Zeta. Okay. So, xi is equal to 1. So, that means if you look at this particular term, if xi is equal to 1, what does this become? This becomes xi omega minus omega squared, right. So, I can actually rewrite this entire thing in this following format. Let us just go back to that solution and let us look at S is equal to, now C upon minus C upon 2 m is minus xi omega plus minus, okay, omega is going to come outside, square root of xi squared minus 1. This is what that solution turns out being. Okay. So, if you look at it, this equation here, by substituting the fact that C upon 2 m is xi omega, I have substituted that into this equation and I have got this equation. And therefore, we basically have this situation that if xi is greater than 1, then we have 2 real roots. And what does xi being greater than 1 mean? That means C is more than C critical, which basically means we call it as over damped. Okay. Then if we have xi equal to 1, then we have the situation that S is 1 real root. This is known as critically damped, because xi equal to 1 implies that here over damped means xi is greater than C critical. Note that C critical is equal to 2 m omega. If C is equal to C critical, xi is equal to 1, and that is known as critically damped. And if xi is less than 1, then S is 2 complex roots. C is less than C critical, that is why xi is less. This is known as under damped. Okay. So, this is essentially, so therefore, a new critical parameter called xi. Xi defines the damping in the system, because xi is equal to C, which is the dashpot constant, upon 2 m omega. Okay. And this particular parameter xi is very important, because if xi is greater than 1, the roots of the equation S are both real. If you have xi equal to 1, which implies that you have a critically damped system, you have S only one root, and that root is minus zeta omega. Okay. So, there is only a single root, S is equal to minus xi omega, and you have under damped where xi is less than 1, in which case both the roots are complex roots. Okay. So, let me write down those roots. So, if I have xi greater than 1, the roots S1 is equal to minus zeta omega plus omega into xi squared minus 1 if xi is equal to 1. Sorry, here then you have S2 is equal to minus zeta omega minus omega square root of xi squared minus 1. If xi is equal to 1, you only have one root, which is minus xi omega. If xi is greater than 1, you have two roots. One is minus zeta omega plus minus I omega 1 minus xi squared. Note that 1 minus xi squared is a positive quantity, because xi is less than 1. Okay. When S2 is equal to minus xi squared, sorry, this is plus and then minus. Okay. So, let us look at the overdamped system. What is the solution? The solution is the overdamped system. The solution is u of t is equal to a1 e to the power of s1 t plus a2 e to the power of s2 t. And so, if I can I will substitute these two values, okay, and note that if s1, this is exponent and you have minus and plus, what that becomes is that we can rewrite this equation in this form: e to the power of minus xi omega t into a1 e to the power of omega xi squared minus 1 t plus a2 e to the power of minus omega into xi squared minus 1 t. Okay. So, if we in this particular equation, if you look at it, what does this represent? And of course, how do I get a1 and a2? Well, I can get a1 and a2 by substituting u0 and u dot 0 into these equations. Well, how do you do it? You find out u of t, plug in, put equal to 0, okay, and you know this will be e to the power of 0, 1. So, this will be 1. So, it will be a1 plus a2 is equal to u0, and then similarly you can differentiate u of t of time. I am not going to go into this. I am not evaluating the overdamped system response. Okay. I am just writing it down to show you what actually is the form. The form, if you look at it, consists of two terms, one an exponentially exploding function, one an exponentially decaying function, superposed with an enveloping exponentially decaying function. And if I look at this, I am going to only draw it qualitatively. You can, if you are interested in, look at any of the two books that I have talked to you about, and you can see what the solution is by substituting. You can get a1 and a2, but I just want to show you qualitatively what this looks like. Initially, the exploding function takes over, and then this function essentially starts kicking in, and what we have is we have an exponentially decaying function. Okay. So, this is how an overdamped system free vibration looks like. Note that, do you see any vibration here? No. You know, the free vibration term is actually a misnomer for an overdamped system, because an overdamped system, if you give it an initial displacement and initial velocity and it's overdamped, what it will do is it will go like this and slowly come back to this. A classical example is an automatic closing door. Have you seen it? You open it and then it slowly closes. Okay? That is what happens. There is no vibration. So, an overdamped system, an overcritically damped system does not vibrate at all. It does not vibrate at all. It just exponentially goes up and then exponentially decays. That is what an overdamped system is. Okay. Now, I just want to here itself show a critically damped system. Without going about it, since a critically damped system only has one root, okay, the solution u of t is actually of the form a1 plus a2 t e to the power of minus zeta omega t. This is how it looks. Okay. Now, if you look at this, this is a linearly exploding function superposed with an exponentially decaying function. So, what this looks like, if you give the same initial displacement and same initial velocity, what this will do is this will go up like this and come back. A critically damped, look at it, a critically damped system has a linear exploding function and then slowly the exponential decay takes over after a period of time and it comes down very, very quickly, because note that here you have an exponentially exploding function. Here you only have a linear exploding function. So, once this function takes over, okay, this comes down really, really quickly and goes to 0 really, really fast. So, this, the only difference between an overdamped system and a critically damped system is that both do not vibrate. Both, when they are subjected to a initial displacement and an initial velocity, go up, okay, and then come down. The reason why this goes up more than this is that even though you have an exponentially decaying exploding, it is added with an exponential decaying function. So, actually a overdamped system response is lower than a critically damped system response, but once the exponential takes over, okay, here because you have an exponential exploding function, this goes down much slower. This one takes over and this comes down. Now, you can actually get A1 and A2 and you can actually plot these yourselves and you will see that what I have shown qualitatively is what you get. Okay. So, I am done with overdamped and critically damped systems, and note that they do not vibrate at all. Okay. The thing is, an overdamped system goes like this, takes a long time to come back. A critically damped system is less, because zeta is greater than 1 for an overdamped system. A critically damped system goes further, comes back quicker, but still does not go in the other direction. Note that all of them are positive. So, that means, if I let them go in this direction, they will only come back to 0. They will not go back this way. So, there is no vibration. Okay? So, an overdamped system and a critically damped system do not vibrate. Now, why am I not interested in the solution? Because in a structure, we do not get, fortunately, an overdamped or a critically damped system. A structure always is under critically damped, underdamped system. And so, in the next lecture, we are going to be looking at how to look at a solution of an undamped system and see how we can solve that. Okay? Thank you. Bye.